Alright, so this week we are going to go over chapter 9, reactions of alkyne. Okay. So just like chapter 8, there's quite a bit. And just like last time, I won't be particular about the names. I do think the names are important, and I would know it just in case it comes up on a quiz or exam. Beyond that, any other information I would ask your professor. Alright, so let's start off with the first one, and that is going to be, so let me draw the structure. Just for reference, we have about 26 of these to go, but I'll be going over fairly quickly, and I'll explain all of them as to my best of abilities. And not every single one of them, you have to know the mechanism. If you are interested, I would refer to your PowerPoint as well as your textbook. Okay, so we have a triple bond here, and at the very end we have a hydrogen. Okay, and the reaction above the arrow is, we have two parts, so NaNH3. The second part is CH3 iodine. Okay. Any ideas what this reaction will do based on the starting and the reagents? Let me know if you guys know in the comments. Okay. It forms an alkene. Okay. Not quite. Any other guesses? Okay, in the meantime, I'll draw the next one. So actually, we're just going to use the same one, so I'll just draw an arrow this way. Hydrogenation, okay. Not quite either. Okay, give me 1 second, I'll tell you guys what it is. So this one is also NaNH2. Okay, sorry, this should be NaNH2. Oh, and I guess we are zooming in. So that should be NaNH2. And then this second reaction should be, well, actually, I can't write that out, so I'll just put that. And then for number 3, it's just going to be acidic water. Okay. And then for number 2, we actually just have a ketone. Okay. All right, so the first reaction, what's going to happen is the purpose of NaNH2 is going to act as a base. Okay. And what do bases do? They deprotonate and accept protons, right? So it's going to remove this hydrogen from this triple bond, and that's actually very good because triple bond, this is a very acidic proton, so it's going to want to donate to a good base like sodium amide or amine. So once we have a negative charge here, that negative charge is going to act as a nucleophile and attack this electrophile. Okay, this iodine should tell you that this is some type of electrophile, and the iodine is the leaving group. Okay, so whenever you guys see this, think in terms of, last unit where you have a nucleophile and an electrophile. to kind of help you guys with the reaction. Okay. So even though there's a lot of reactions this unit, there's still ways to identify what to do. So I'll kind of show the first step. The first step is where we get rid of the hydrogen and form a negative charge. And then obviously the next step is when that methyl group attaches on. Okay, so this is very useful whenever we need to add extra carbons. Okay, all right. Also, you guys should know this already, but whenever you guys see a triple bond in between, make sure you guys understand that there's here, let me actually type in all the different carbons. I'll just do it once and then we'll just use that for reference. So there's carbon 1 right there, 2, 3, 4, okay? And then in our final one we have 1, 2, 3, 4, 5, okay? The fifth one came from our reagent, okay? So in a similar fashion, this one, the first reagent is the exact same and we have the same starting compound. So we're still going to remove our hydrogen. Then this as our nucleophile is going to attack this ketone. Okay? Now, in the past, you guys are used to a carboanion attacking a carbocation. Okay? But in this unit, what you'll find is a carboanion can also attack a carbonyl. Okay? Basically, anything negative with a slightly negative charge can attack a slightly positive charge. Okay, and carbonyl has that dipole moment, which I will draw a little bit bigger to show you guys. Okay, so it creates a dipole moment because oxygen is negative or more electronegative. Our dipole moment is going to go this way. Okay, so we have a S negative here and a S positive here. So we have a partial positive charge here. So that's why carbonyls, so any ketone, aldehyde, amide, carboxylic acid, any of those are susceptible to nucleophilic attacks. So when that happens, I'll showcase that real quick. So what we have here is, I'm going to redraw this. So this negative charge is going to attack the carbonyl right there, okay? And when it's going to attach right there. And if we form a new bond right here, something has to go, right? So that's why the electrons are going to move to the oxygen. So we have a O negative. Okay, so this is where we are right now. Okay. And then eventually that O negative will turn into alcohol, okay, something called proper workup. So basically, imagine a water molecule in the solution donating one of its hydrogens to this negative charge. Okay. So in the very end, you get something that looks like this. So we have our triple bond here. and that triple bond formed a new bond between the triple bond and the ketone. So I'm going to denote that in green. And then the rest of this, we have two methyl groups from our ketone. And then remember, instead of a carbonyl, we now have a alcohol, okay? And then I guess I'll type this in. OH, yeah, proper workup. Okay? Zoom out a little bit. All right. Does that kind of make sense? Any questions on any of this so far? All right, so let's move on. So next, these two questions are going to be, or two reagents are going to be very similar to each other. Like I mentioned last week, the best way to learn these reactions is just to repeat it over and over again, and that's how you remember them. And another way is to group all those reactions so you can remember them better. Okay, so next up we have a halogen here and a halogen here. And then these are hydrogens. So this is a four-membered carbon ring. Okay. So with this, and this also is the starting compound for this next reaction as well. So the first reaction is H with heat. The second reaction is NaNH2. Fix that. With heat. And then at the very end, we have water. So the KOH1 will form a what we call internal alkyne. Okay. And then the NaNH2 with heat will form a external alkyne. Okay. And the reason why we're going from alkane to an alkyne is because of this heat. With one addition, we will remove, so these are strong bases, okay? And we are performing elimination, okay? That's how we get from alkane to alkyne. We have to perform two additions of elimination. Okay, and I'll write that down right here. Two elimination. So in one round, we are getting rid of the halogen and adjacent hydrogen. And the other one, we are getting rid of a halogen and an adjacent hydrogen. Okay. And these two have specific temperature, actually. So sometimes they may be paired with, so KOH will usually be 200 degrees Celsius with 200 C, and NaNH2 is usually paired with 150 degrees Celsius. Okay. That might be a conceptual question. I'm not sure, but just in case. Okay. Now, what it actually looks like by internal and external, even though they have the same starting compound, the different bases and the different temperature results in different locations of the triple bond. Okay? So for alkyne, remember we had 4 carbons, so we're still going to end with 4 carbons because we're not adding any extra carbons. All we're doing is placing another like pi bonds and eliminating these. Okay, so the first one is going to look just like a straight line because it's supposed to be internal. So just another quick, I guess, little bit of information is triple bonds are always on plane. They will not bend or they will not have stereochemistry, just like double bonds. But triple bonds especially want to be flat and always going to be straight. Okay. Now for the external alkyne, it's going to look like this, where we have a triple bond between carbons 3 and 4 rather than 2 and 3. Okay? So depending on what you need, external or internal, your reagent will change. Okay, and you have to know both of these because both of these could be answer choices. Okay? So, this is a set of questions. This is another set, like grouping wise, like reactions wise. Okay, and then we also have another 3, and all of them will also have similar starting compound. So we're going to use this example again. So give me 1 second. Yeah, so, wait, sorry, I didn't draw that right. Okay. Just pretend it should be on the same line. Okay, there's no bending. All right. So we are using that for these next 3 mechanisms. And so all of these are known as reductions or reducing agents. So that means we are going from a triple bond and reducing it to either some kind of double bond or some kind of single bond. So the first one you guys kind of already know. It's our H2 PT. This is a simple hydration. And I'll just go ahead and do this one. So whenever you have hydration, that means you are adding hydrogens to all of these bonds and turning everything into alkanes. So once again, let's count our carbons just to double check. So we have 1, 2, 3, 4, and then 5 at the end. So when I draw my hydrogens, I'm going to kind of bend my carbons to show the different carbons. Okay? Because if you simply get rid of this triple bond, it just looks like you have 1, 2, 3 carbons. It looks like ethyl, right? And what you actually want is a pentane or pentyl. Okay? So whenever you get rid of the triple bond, you have to bend your product in some shape or form. All right, so the next one, it's a very unique one. It's called Lindlar's cat, cat catalyst specifically, but I'll just try to ask cat because that's something you might see. And let me slightly scooch this over. Okay. And then the last one is sodium on top and Na or NH3 on bottom. Okay. So don't get that confused. So NaNH3 is very different from NaNH2. Okay, and the difference is in one single hydrogen. Okay, so it's very easy to get that confused, but please don't. All right, so the differences is that one creates a trans double bond transalkene, and another creates a cis alkene. Okay, anyone know which one's which? Okay, someone said Na is trans. Yes, that's definitely correct. So transalkene, the cylinder catalyst is going to be cis alkene. And the way you can remember is that cis stands with C and cat also stands with C. Okay? And then I'll actually draw it out. Remember, we want 5 carbons. We have a triple bond here. And then same thing here. Here we have a, sorry, I meant a double bond. We have a double bond there, we have a double bond here. And then if you count all the carbons, it should match up. All right. So once again, these are very useful because it goes from a triple bond to a double bond, and obviously you can go from a double bond to, once you have this double bond, you can do any of those chapter 8 reactions, okay? So in your final exam, there might be synthesis questions where you have to manipulate from any given starting compound to any given ending compound, okay? So this last unit, there is a lot of reactions, and I will be honest, it can get very challenging. But if you like puzzles, it also becomes very fun. Because synthesis, and you are really getting into what like organic chemistry is when you thought about it before this class. All right. So any questions on any of these? These are fairly important. If not, I'll move on. The rest of these aren't too bad. Let me see. So the first one, again, we have the same compound, 5 carbons on the triple bond between 3 and 4. And then the reagent is, so the first one, I'm going to draw it this way, is 1 EQ of Br2. Okay? So as you know from last week in chapter 8, Br2 adds 2 bromines anti-addition by breaking a double bond. Okay, so in this case, it's going to break one of these bonds. So it's going to go from alkene to alkyne to alkene, and it'll place bromines on opposite sides. So what we end up with looks like this. So we have a triple bond there, or sorry, a double bond there, and we have bromine on opposite sides. Okay. So Br2 just by itself, or Br2CCl4, is going to be anti-addition. Sorry, that should be bromine, not chlorine. Okay. And just as a reminder, feel free to stop me at any point and just ask questions if you're lost. Hopefully this should be a review, as all of these weekly reviews should be, just to supplement your lecture. All right, so what we are going to do now is we're going to have another equivalence of Br2. So from the very beginning, imagine the arrow said 2 equivalents of Br2. But because we're going from this compound to the next one, that's why I just said another equivalence. Okay. So if we add another round of Br2, we are now going to break this double bond and place bromines again opposite to each other. Okay, so nothing fancy here, just going to add bromines on opposite sides. So we are essentially having 4 bromines. That's slightly messy, but you guys get the picture. Okay. Let me see if I can fix this. All right, and sorry, just wanted to fix that. Okay, there we go. All right. So, we can also have a HBr. So I'm just going to draw that right here. And this is just one equivalence of HBr. Obviously, if you have multiple equivalents, we'll have more. So remember, HBr by itself is going to attack in the concave position. Actually, hold on. This needs to have. So we have our triple bond here, but instead of a methyl group at the end, we're going to have a hydrogen to showcase a less substituted side and a more substituted side. Okay. Instead of arrows, I'm just going to write HBr. This is 1Q. So, like I said, it's going to be more concave. So we are going to break our double bond and add bromine at the more substituted side, which is going to be on the left side. Okay. So remember, it's like we have 1, 2, 3, 4 carbons. So 1, 2, 3, 4 carbons, and then we have a more substituted side and less substituted side. So that's why we took one of the bonds and added bromine on the side. And then if we do another addition of hydroboration, another equivalence, once again, it's going to be more concave, so we are going to add bromine on the other side now. Okay. So it should be fairly similar to what we just did with the Br2. Okay. So these are other ways to go from a triple bond to a single bond by adding bromines. And once you have this bromine, remember, you can do elimination, you can do SN1, SN2, you can do lots of things with bromine, okay, because it's a good leaving group, okay? So just start to think about different ways you can manipulate the mechanism. All right, and obviously, if we have HBr peroxide, which is H2O2, we will get the same thing, except Br2 will be on the other side, like that. Okay. All right. So, any questions on any of this? I might have to clear the board actually. So, you guys need to quickly copy it down or take a screenshot. I'll give you guys a couple seconds to do that. Is anyone else copying? For those of you guys who are in the room, can you guys type in OK once you're done to move on? Okay. All right, so we just have about 7 more reactions. They should be fairly quick. So I'm going to clear the board. Okay. In case you didn't get everything, obviously just go back and watch the YouTube recording of it. All right. So these are slightly tricky, or trickier than what we've been dealing with. So we're going to have the same common starting compound. Okay. And the reaction is HgSO4. And underneath it, we have H2SO4. Okay. So, difference is the G versus the 2, so don't get that mixed up. So what this will do, and this is actually something what we call keto-enol cautionarization. Okay, you guys might have heard this in lecture, so I'll type it out. So it's keto-enol let me check the spelling real quick. Okay. All right, so keto-enol polymerization. Obviously, keto means ketone. Enol means a alcohol. That's where the OL is coming from on a double bond. That's where the EN is coming from, and I'll draw it out for you guys. Okay, so what this reagent will do using this triple bond, will turn it into a ketone, and we are gonna add oxygen on one of these double bonds. Okay. So first, it will go into the enol formation, like this, where we have where it will add alcohol in the Markovnikov position. But this isn't the most favorable position to be in. Enols really prefer to be in the keto position, so we are going to essentially rearrange, and the fancy word for that is like polymerization. So we are turning this enol into this ketone. Okay. So as you notice, it should have the same amount of carbons. Also, sorry, this should be a hydrogen at the very end. Okay. So 4 carbons here, 4 carbons here, 4 carbons here. This is acidic sulfuric acid. We are adding a alcohol to the more substituted side because it's acid. Acids will always go on the more substituted side. And then, yeah. So this might be one of those where you don't necessarily need to know the mechanism. So if you want to just remember the ending product, that's perfectly fine. This next one, we're going to use the same reagent, starting compound. The first one is called Ca2pH, and then underneath it is H2O2, which is peroxide, as well as NaOH. Okay. So with this is also another of those keto enol polymerization. But the difference is we are actually doing it on the less substituted side, the anti-Markovnikov side, because of this peroxide. So just like before, or unlike before, we are going to have something that looks like this. We have our double bond there, and we have our alcohol here. And we are going to rearrange that into a ketone. Or instead of a ketone, because there is a hydrogen here, we are going to actually get a aldehyde. Okay? But the principle is very much the same. Okay? Have you guys done this in class also? Or is this kind of new? Okay, you guys have done it. Okay. All right, so hopefully you guys, after getting a second look, hopefully it's clicking a lot better, and you guys are able to, or you guys are better prepared for the quiz. Okay? All right, so these last 5 ones are going to be cleavages. Now, in the previous week, we've dealt with cleavages using a double bond. Now we're doing cleavages using a triple bond, okay? And it's pretty much the same idea, but it's slightly different, okay? So for the first reaction, I'm going to redraw, and it's going to be the same starting compound as always. All right, so the first one is going to be KMNO4, and we are using water, and it's going to be in neutral conditions. And let me actually draw out all of these, and then I'll draw out the products at the very end. Okay? So the second one is going to have a methyl at the very end. And then this one is going to have hydrogen. And then I'm going to draw another one that has, instead of a methyl group, we are just going to have any R group. Remember, R group is any carbon chain. Like it could be a benzene ring, it could be like a methyl, ethyl, pentyl, it doesn't matter. Then we have one last one, which is going to have the hydrogen at the very end. Okay. All right, so now I'm going to write down the reagents. So after these 5, we're done, by the way. So most of these are going to do with KMNO4. And as you guys know, KMNO4 is a strong oxidizing agent, which means it prefers to create carboxylic acids. Okay? So for the first 2, we're going to have the exact same reagent. The starting compound is different. These last 3, we have KMNO4 with KOH at the top, and we have in warm conditions this time, and water at the bottom. And then likewise the same thing. Here we're just looking at the differences between hydrogen and R group. So KOH, and at the bottom we have warm water. All right. And then last but not least, we have ozonolysis, which is O3. And then at the bottom, we just have regular water. All right. So most of these are going to be very similar. But as you guys know, KMNO4 is a strong oxidizing agent. And let me write that down. KMNO4 equals strong oxidizing agent. Ozonolysis, on the other hand, equals weak oxidizing Okay, so that means if KMNO4 reacts with a hydrogen, it will turn it into a carboxylic acid. If ozonolysis reacts with a hydrogen, it will turn it into a aldehyde. Okay, but that was the condition with double bonds, what we observed last week. So let's see how triple bonds slightly affect that. Okay, so going back to black, let me redraw this. Okay, so this one has 1, 2, 3, 4. So it has 4 carbons, and on carbon 3 and 4, we actually have double bonds, or carbonyls rather. Carbon 4, the very last carbon, will turn that into a carboxylic acid, because this will oxidize into a carboxylic acid, and obviously internal carbonyl will stay as a ketone. Now, if we have a methyl instead of a hydrogen, obviously that cannot turn into a carboxylic acid, so it's going to stay as a ketone. Okay, and let me draw that real quick. So we essentially have 2 ketones. Okay, and this kind of makes sense because, you know, triple bond, we have essentially 2 pi bonds where we can add oxygens to. All right, so this was in warm/neutral conditions. Sorry, water/neutral conditions. So let's see how that affects if we, you know, heat it up slightly and in more acidic conditions. Okay, so same scenario. We are in, sorry, not acidic conditions, just warm conditions, because we are using KOH, which is a base. So the difference here is it's actually going to split it up into 2 separate parts. So on one side, we will have a carboxylic acid, but the rest will evaporate as carbon dioxide because of this second step right here. KOH, or sorry, warm H2O, warm H2O. Okay, and that's going to be the case also for this R group. Let me double check. So it's going to be slightly different. Almost done. So CO2, just for reference, so you guys know what it looks like. It looks like this. The positive charge here and a negative charge here. Now the difference here, because of that R group, we will have alcohol here, carbon, carbon here, R group here, and oxygen here. Okay. All right, and then last but not least, ozonolysis. Because it's triple bond, and ozonolysis is usually will create aldehydes. That will not be the case for triple bonds. It will also create a carboxylic acid. So that's the thing you have to know and remember and not get confused with the double bond cleavage. And then the difference here is the side product. When you cleave it, you will get an aldehyde instead of the R group. Okay? Do you guys have any questions on any of these? These might be slightly more challenging from the first page, but they are equally important And yeah, I'll wait a couple minutes just in case you guys have any questions, anything you want me to go over. But otherwise, we're done. Thanks for coming or watching wherever you are present here. And I'll see you guys next week for chapter 10 when we get into alcohols. Okay? And just as a reminder, the final weekly review is going to be November 24th. So next week we'll go over chapter 10, which is alcohols, and the week after that, I might do like a exam review or like a final exam review. Yeah. Yeah, thanks for coming. For those of you who are attending live, and for those of you who are watching on YouTube, I will see you guys next week.